Hello and welcome to the presentation of our work for this year's ICONIP. My name is Adriano Lucieri. I'm a PhD student at the German Research Center for Artificial Intelligence in Germany. Today I will be talking about methods for concept localization that bring us a step further towards understanding deep neural networks in complicated application areas like medical image analysis. First, let me introduce you to Cadis. Cadis is one of the world's best dermatologists and brilliant in detecting skin cancer. However, Cadis is not able to speak, nor can he move his body to, for instance, point somewhere. Most importantly, he does not share any common concepts with his dermatologist colleagues. All of this makes it really difficult for Cadis to express his thoughts and explain his decisions to any involved stakeholders like patients, colleagues, and authorities. This in turn results in low trust from stakeholders and also in questions of accountability. As you might have already guessed, all of those issues are the case with current deep learning-based CAD systems, short for computer-aided diagnosis. And this constitutes a major barrier in their clinical deployment to support human doctors. What makes all of this much more problematic in the medical domain is that medical image datasets usually deal with extremely complex problems that usually require a lot of experience and education to solve. Taking dermoscopy of skin lesions as an example, dermatologists use complex concepts that can be very subjective and hard to grasp for the diagnosis of malignant cases. Here are some exemplary concept definitions. Pretty ambiguous, right? Those concepts include patterns in the color or in the pigmentation structure and are also intertwined with symmetricity. This poses a lot of problems to AI and XAI researchers who want to advance methods for the medical image domain, but struggle to understand the problem itself. Usually, concerted collaboration between doctors and developers is required, which is good on one hand, but also protracts the process. Let's get back to Cadis. Actually, there already exist some methods that aim to mitigate some of his limitations. His inability to point to input regions can be mitigated using attribution methods visualizing most relevant input pixels. Common concepts can be derived by applying concept-based explanation methods like testing with concept activation vectors, which quantify the presence of a concept in an image, as well as the contribution of a concept to a class prediction. However, it was just mentioned that the complexity of medical image datasets is quite high, containing very subtle and overlapping concepts. Thus, simple attribution maps don't really suffice to provide clear and unambiguous explanations. A more fine-grained method for concept localization is required to verify the quantitative metrics provided by TCAF, making sure that the DNN understood concepts right, and provide useful hints for doctors in a computer-assisted diagnosis setting. In our work, we started with asking the question whether it is possible to localize individual human-defined concepts that have been learned by the DNN and identified through the TCAF method. Therefore, we first wanted to tackle the problem of high dataset complexity in medical problems, as working with a medical dataset would again lead to ambiguity. We introduced a new synthetic concept dataset that imitates the complexity of dermoscopic skin datasets. The dataset abstracts a skin lesion through base shapes that contain a bunch of smaller concept shapes. The classification result is solely depending on the combination of concepts that lie within the base shapes boundary. Second, we use SCDB to develop our proposed method called concept localization maps. The method combines parts from TCAF together with the idea of attribution methods. We tested 3 variations of the method and identified one as working best. Then we transferred the method to a real-world dataset to initially prove its practicality. Here we can see some results for the localization of the ellipse concept in different images. Each CLM heat map is clearly able to locate the ellipse in the samples. Here we can see 3 different localization maps generated for 2 samples. Each localization map is able to locate the desired concept, even if concepts are overlapping or occluded. Finally, this is an example of concept localizations generated using the CelebA dataset. Left-hand examples show localizations for the concept bald, and right-hand examples for the concept lipstick. It can be observed that the DNN correctly learned to highlight a person's bald forehead for the bald concept, and the mouth area for the lipstick concept. This was a short overview of our work. Now let's take some time to dig deeper into the proposed dataset and our CLM method. As mentioned before, our first contribution is the generation and release of a synthetic dataset that imitates some of the complexities of medical image datasets in a controlled and understandable environment. SCDB includes 10 different concepts, abstracted by transparent colored shapes that can overlap. The data is categorized in 2 different classes, depending on the combinations of concepts which are present in the base shape. 2 of the concepts are control concepts which are not necessary for classification. Each image is annotated with target labels and additional binary labels for every concept type. In addition to that, we provide segmentation maps for each individual concept per image. Using this synthetic dataset, we developed a method to localize concepts in input images of DNNs. As I mentioned, the method is based on the concept-based explanation method TCAF, as well as on attribution methods for DNN explanation. We first start by training a usual convolutional neural network using the training images from SCDB. Once the network performs sufficiently on the main classification task, we are interested in the role of concepts during classification. For each concept, we want to know whether the network is able to recognize the concept if it appears in an image. The idea of TCAF is to show the network a bunch of images that are labeled as containing star and others that do not. If a linear classifier on top of any intermediate layer of the network is able to succeed in this task, we can expect that the concept is implicitly encoded in the network's representation. So let's take a step back. We trained our classifier and will now train linear concept classifiers for each concept. Therefore, we use our dedicated concept set from SCDB dataset and plug linear SVM classifiers on top of any of the intermediate layer outputs of the network. In this example, we trained the star concept classifier on labeled data that contained star shapes and data that didn't. If the concept has been encoded in the network, we should see a working star shape classifier now. Let's briefly introduce 2 attribution methods. The occlusion method was introduced by Seiler and Fergus in 2014. The idea is as simple as systematically occluding input regions, using, for instance, a black patch of pixels in a sliding window fashion, and iteratively evaluating the occluded images through the DNN. The changes in output probability are recorded together with the spatial location of the patch. The result is an occlusion sensitivity heat map that is able to locate the most relevant input regions. The second attribution method simply computes the gradient of the loss function with respect to the input pixels to obtain a relevance map. In order to reduce noise in the relevance signal, we applied the smoothgrad and vargrad methods that simply re-evaluate an image multiple times while adding noise and averaging the results to mitigate noise. We used the aforementioned explanation methods in combination to propose 2 completely new concept localization methods. The first one, called PCLM, uses the perturbation-based occlusion sensitivity method. Instead of recording the output probability of the classifier, we now use the changes in concept prediction of the linear concept classifier to localize a corresponding concept. Our second proposed variation of CLM is called GCLM and is gradient-based like the saliency method. Instead of computing the gradient of the correct output class with respect to the input image, we compute the gradient of the intermediate activation layer used for concept computation. However, we do not compute the gradient of all latent dimensions, but only those of those most relevant to the concept classification. Therefore, we use the weight vector that has been trained during the optimization of the linear concept classifier. By applying a thresholding scheme that retains only the most relevant 10% of activations, we generate an activation mask that is used to filter only relevant activation dimensions. We now compute the gradient of the remaining concept relevant dimensions with respect to the input image and obtain a gradient-based CLM map. As mentioned previously, we also applied the iterative smoothgrad and vargrad techniques to reduce noise in the heat maps resulting in 2 variations of this method. We quantitatively evaluated the method on our SCDB dataset using the generated ground truth concept segmentation maps. 3 different network architectures have been investigated. The metrics show PCLM constantly outperforms the gradient-based variance. Also, we see that more complex architectures like SE-ResNext50 improve localization and show more constant concept representation behavior over different layers. A best IOU of around 26% for concept localization has been achieved, as well as a recall of over 68% with PCLM on SE-ResNext50. This evaluation is not perfect and does not reveal the full potential of the method, because first we evaluated the localization performance of all 10 concepts, including 2 non-relevant concepts. Each recall on all of the 8 positive concepts scored over 80% though. Moreover, the IOU is a hard measure, which is a drawback for the evaluation of fuzzy heat maps. Finally, the optimization of the GCLM heat maps as well as the binarization of CLMs for evaluation are threshold-based and non-optimized. We are already working on improving our methods and evaluation techniques. But now let's again have a look at the qualitative evaluation. Here we again see the localization maps for the concept ellipse on 4 samples. The reason for PCLM being superior in quantitative evaluation are obvious. GCLM heat maps are much more sparse in their nature and not always succeed in localizing only the desired concept. Here we again see the three different perturbation-based localization maps generated for 2 samples. It is striking how PCLM is selective enough to always pinpoint the right region, even if concepts overlap. It is also interesting to note the potential failure case in the 3rd column of the top row. The model recognized the occluded orange hexagon behind the yellow rectangle as a pentagon as well, probably because it just saw 5 corners. The evaluation on the CELAB-A phase dataset revealed more superiority of PCLM. Here we see again the bald concept and how with PCLM we are able to localize the forehead of people. Also, the rightmost column shows that the network seems to sometimes confuse the concept of heads with the bald concept. Finally, this example shows how the PCLM is reliably able to locate the mouth region for the lipstick concept, whereas the GCLM method often erroneously focuses on the eyes as well. Let's recap everything. Our 2 main contributions include the release of a public and synthetic concept dataset that is inspired by the complexity of medical dermoscopy datasets. Moreover, we used the dataset to develop a method for reliable localization of concepts, learned by the DNNs. This method is useful for validation of identified human concepts in DNN, as well as reliable concept region suggestion in AI-based decision support systems. For our future work, we will be focusing on improving the method by using optimization-based perturbation to obtain more fine-grained and precise heat maps. Also, we will improve thresholding to obtain a more meaningful quantitative evaluation. The final goal is the application of the medical problems like, or is the application to medical problems like dermatology and radiology. CLM will be further developed by our team at DFKI and TU Kaiserslautern and soon applied to medical computer-aided diagnosis scenarios. Thank you very much for your attention and feel free to ask in case of any questions.